Boom. Hello and welcome back to Calculus 3. This is the second part on our change of variables, 13.7 last section. So the last class we talked about the transformation of region, which was equivalent to changing limits of integration from your U sub. We have one more piece to discuss, and that is the Jacobian matrix, because remember, when you do your U substitution, this is what was done last time. When you do your U substitution, you have your transformation, and then you have your derivative, and then you have limits. So this is transforming the region portion is equivalent to that. Your transformation is given here, and this will be the Jacobian matrix equivalent of the part. So we have all of those together. All right, let's take a look at what we need. So first of all, Jacobian determinant, Jacobian matrix. Is the matrix of partial derivatives. So partial xy, partial uv, and it's the matrix of partial x, partial u, partial x, partial v, partial y, partial u, partial y, partial v. So that's the Jacobian determinant. You know how to solve these determinants. I will erase this. You will push through and then go out the other side with a minus in between and multiplication symbol, right? So you know how to compute determinant of 2 by 2 matrix. And now we can finally write down the theorem for the change of variables in double integrals. So whatever integral you get over the region which you cannot compute for whatever reason, and you have the transformation that would work, you will transform region R into region S using that transformation. You will then use the transformation to transform your function f using the functions g and h. Multiply that by the Jacobian, right? And you will have dA, which is on the new dA that is now du dv. So the entire integral now becomes, in terms of uv, your region is uv, everything changes to the new domain. So let's look at the examples. They have separate examples for computing Jacobian and so on. You know how to take partial derivatives and do that 2 by 2 matrix. Let's take a look immediately at these problems. So I don't know, whatever, it's all look the same. 28. Double integral over region R for x squared y dA, where the region R is given 0 less equal than x less equal than 2, x less than y less than x plus 4. And then use transformation x is to u and y is equal to 4v plus 2u. I hope you started a new notebook. It's all right. So first order of business is to draw region R. Without that, technically dead in the water. So I have y equals x and y equals x plus 4. So these are the two lines. They're parallel linear lines. And then we have 0 to 2. So this is our region. The red parallelogram here is our region R. Now this is in the XY realm. We want to change this into UV. So I want to see what I'm going to get on the UV plane once the transformation is done, and that would be region S. So what do I have? I have sections 1, 2, 3, and 4. Guys, you haven't done these transformations before, so you should really follow the easy steps without skipping stuff. Let's transform number 1. So what do I have for number 1? I have y equals x, and x is stuck between 0 and 2. So what is u equal then? And what is v equal to? Well, if you look at this transformation here, it is sometimes helpful to solve this transformation into uv. So u equals, and you see it's x over 2, and over here we start with 4v is equal to y minus 2u. 4v is equal to y minus, and now 2u is just x. So v equals u minus x over 4. So sometimes you have to use systems of equations to get this done. Sometimes you can just massage a little bit around these equations and you get v and u and v equals everything else in terms of x and a y. So now we know that x was equal to 2u. So the first equation can be transformed as what? Well, we are only allowed to have u's and v's. So if you are to, so this is, the issue with this is there are no rules. You just have to look and see what you're going to get here. You see how if you move this, you get y minus x equals 0, right? And you see over here y minus x. So we have, this equation gives us 4v equals 0. v 0 at all times.
Can you not say that y also equals 2u? Or no?
Y equals 2u. Yeah, but doesn't help.
Why not?
Because you have y, no y's. Everything has to be v's and u's.
How is it not that 4v equals 0?
Because when I move this equation to get the one below, I see here the same structure, y minus x and y minus x. So y minus x is equal to 4v when I move the 4 to the other side. So v is equal to 0. And over here, I have 0 less than x is 2u. So 0 less than u less than 1. So I will go on u from 0 to 1. And v will always be 0, so I get little part there. 0 to 1 is just a flat line. That's line number 1 transformed. Now we move to number 2. It's a lot of fun, right? For this one, x is always 2. And y is stuck between 2 and 6. Do we see that? So x is always 2 and y is stuck between 2 and 6. So x equals to 2. Well, x equals 2u, so 2 equals 2u. So u equals 1 all the time. And y, what's y equal to? Y is 4v plus 2u. Can I do this in any better way? So I have 2, and instead of y, I can put 4v plus 2u less equal than 6. So if we divide everywhere by 2, we get 1 less than 2v plus u less than 3. Now u is, what's u? U is 1. So u is equal to 1. So I have 1 less equal than 2v plus 1 less than 3. Then we take away 1 everywhere. 0 less than 2v less than 2. And divide by 2. So v is stuck between 0 and 1. U being 1, we get that much. That's 2. 3. 3 is this line segment again. We have x to go from 0 to 2. And so x goes from 0 to 2. And what's y doing? Y is equal to 4x. Y equals x plus 4. Awesome. So what's x? X was 2u. So again, 0 less than u less than 1. And over here, I can again use the same trick, y minus x equals to 4. But y minus x from the blue one up there is 4v. So v is 1. And we get the top. You all know what is going to work, right, to be. You can already see it. It's going to be a square, right? 1, 1, 1. And the fourth part, transformation, our x is always 0, and y is stuck between 0 and 4. So transformation says x equals 2u. So 2u equals 0, u is always 0. And the y is 0. And what was y? 4v plus 2u. But we know u is 0, so that dies. And when you divide everywhere by 4, we get 0 less than v less than 1, which is vertical. So this particular transformation took this parallelogram from region R and turned it into a square region S, a square of side 1, which is awesome. All I need now are partial derivatives for Jacobian matrix, and we can plug everything in. So Jacobian of u and v is going to be partial x, partial u. So that's 2. Then partial x, partial v, which is 0. And then partial y, partial v is 4. And partial y, partial... No, this is 4 and this is 2. I hope. So we have partial x, partial u, partial x, partial v, partial y, partial u. So I'm looking at the functions here on the screen. Partial x, partial u, it's 2. Partial x, partial v is 0 because there is no v. Partial x, partial y, partial u is 2. Partial y, partial v is 4.
Where are you getting that from?
Okay, so first of all, I know the formula for it, right? Which is this.
Just where do you plug in the number? Where do you get the numbers from?
What I'm looking at the transformations. I was looking at transformations on the screen because I have the problem, so I don't have to flip up and down. So I was looking on this screen to get the functions from the problem. So look, partial x, partial u is 2. Partial x, partial v is 0. Then partial y, partial v, partial u is 2. Partial y, partial v is 4. Now, sometimes they're going to end up being functions. Sometimes they end up being numbers, depending on what kind of transformation you have. Determinant over here, 8 minus 0 is 8.
Walk us through that. I didn't use the matrix. What?
2 times 4 minus 2 times 0. Like a cross product.
Oh. Oh yeah.
You haven't used that in a week and a half.
2 times 4 minus
Jacobian.
2 times 0. Okay.
It's x, u, y, v.
I know.
X, y, u, v. X, y, u, v. Look at this. X, y, uv. Whatever helps to memorize. Guys, we are ready to set up the double integral. That's the enthusiasm. Nice. We are on the rectangular region. We have a square, so 0, 0, 1, 1. Right? Our functions have to be transformed from x's to u's and v's, which means that each x will be replaced by 2u. We have x squared, so that's 2u squared. And then we have y. You sound like a witch. 4v plus 2u times 8. And then du, dv, or dv, du doesn't matter because it's a square, right? 0 to 1, 0 to 1. Foil, integrate, and done.
How fast?
No, each problem should take about 20, 25 minutes.
There's only going to be one of these there, right?
The difference between you guys and those who are not learning this is you're learning this and you know. What?
I want to
Just
play.
watch the YouTube videos of people react while playing this.
really
There's a
wanna-
40-year-old guy sobbing, like he's like from mountain, right? The biceps are like 15 feet.
Here, let me.
He's crying, like legitimately.
I really want to play that game, but the thing is, you have like no way of fighting back. So
Exactly.
right, I know that's the point. So now, hang on. Is amnesia? Is it the first one or the second? First one or the second one? Or like there's like that. I think there's like a pool and there's like piranhas or something in it, but you don't know where they are, so you have to like throw human limbs in to. Is it the first one? Yeah. Yeah.
Machine for pigs.
I thought you said the sheep for pigs.
The sheep for pigs.
Yeah, I'm gonna make that.
What's 16 times 8? What's 16 times 8?
Pull out. It's like a concept. Pull it out. Pull it out.
And of course, it's like a dark road all along. Oh.
Pull it out.
Maybe I am a baby.
It's not fun to watch like that, by the way.
I don't remember. I know here's a button.
This one shows the guy who said defensively.
So it's a really quick integral to compute. We have integration in respect to u first. So that's going to be 4/3 v, and then u is 1, plus 4, so 2 u to the 4th, so it's just a quarter, half, right? It will be u to the 4 over 4, so it's a half there, and you plug in 1. dv. So when you integrate, there will be 2/3 plus a half. Iron 32 in front. So I think it's 16 times 7 over 3. Yeah. So 7, 14, so 14, 28, 56, 112 over 3. So one more time, the longest is to transform the region. The rest should go pretty fast. Transforming the region means you pick each edge of the original shape that you have, and you transform each segment, which will give you the new picture, and then you will integrate over that new region. So your variables x and y, your domain x and y now becomes domain uv. Everything is in uv. You have a region in terms of uv, you have Jacobian matrix, which is the derivatives in terms of uv, and then you have to also change the function in terms of uv. So everything has to change because it's a change of variables. Yes? Considerable amount. So let's do one more of these. All right, one more. We have a region R, integral x squared square root of x plus 2y dA. The region R is given 0 less equal than x less equal than 2, and then negative x over 2 less equal than y less equal than 1 minus x. The transformation x equals 2u and y equals v minus u. Again, draw the region first. Try to do transformation. See how it goes.
over time.
Do we all have the same region?
What's the point of this two? It's already intersected two.
Yeah, well, you have to put the region. So yeah, they intersect at 2, so 0 to 2.
What's the point of it if they already intersected?
But you can't just say x equals 0, because x equals 0 would force you to be just on the line. You have to say between 0 and 2, which allows you to shade everything. Also remember that I can say 0 to 3, which means that you would have to go through the intersection and shade all the way up to here. That's possible as well. Yep. Of course not, but yeah. Yes, but no. All right, in blue, u equals x over 2, just in case if we need this stuff. And then and then v equals y plus u, so v is equal to y plus x over 2. So just in case, we'll have these as well ready. Let's go. We only have 3 regions, right? Three boundaries to worry about. So number 1, x is between 0 and 2, and y is negative x over 2. So we are going to replace x with 2u, and we'll get 0 less than u less than 1. On the other side, we know that y is v minus u equals to, and x is 2u, so negative 2u over 2. So we have v equals to 0. So if I'm to draw that on the uv plane, I have this much. I'll use this as 1 unit, and then 2. So I have that much so far. That's 1. Number 2, again, x is stuck between 0 and 2, and y is 1 minus x. So we already know that this is 0 less than u less than 1. And then y over here is going to be what? Y is, what's y? Y is given as u minus, v minus u, thank you, v minus u. And that's 1 minus 2u. So v is equal to 1 minus u, and u goes from 0 to 1. So what now?
To 1.
It would u 45-degree line.
45-degree line. It starts at 1. This. Guys, it is y equals 1 minus x, right? Except now your variables are u and v. It behaves the same way.
leave it as a function of u?
It is, because look, Alex, look at the, this is your main variable now, u. That's your new x. That's number 2. And then line number 3. Line number 3, when you look at the picture up there, x is always 0. And y is stuck between 0 and 1. So when you plug in 2u for x, you get u is 0. And you plug in v minus u for y, but u is 0, you just get, right, this is 0, you just get that v is between 0 and 1, which is just this line.
Okay, I got it. We just exchanged the triangle sine and triangle. Why can we have done it in for region R instead of S? From the get-go?
Yeah.
Not get-go.
Yes. The answer is yes. We can pick much worse problems. These are the ones that are fun to transform and easy to follow as introductory examples. What you have is the lifetime of using worse examples if you want to. Jacobian now.
What's the point of doing all this?
Remember how you can integrate e to the... Remember how you can do this until you do u sub?
Yeah.
Well, this is the u sub for double integrals.
So all this retransformation is possible to do the double integral u sub.
This is double integrals, right? Yeah. Now I'm going to find Jacobian. Jacobian says partial x partial v, no, partial x partial u, which is 2, partial x partial v is 0, partial y partial is -1 and +1, so it's 2. Now this is double integral, and it's not a square now, it's not a rectangle, so we have to think. We are going to transform our original problem. So the original problem was x squared, so that's 2u squared, times the square root of x, which was 2u, plus 2, and then y was v minus u. And now times the Jacobian, which is 2. And then we have du dv or dv du. Now when you are looking at the problem, you want du to be the main one, which means v goes here, so u is going to be 0 to 1 on the outer limits, and the inner limits are 0 to the function, and the function was 1 minus u. This is a ton of fun. So 2 squared is 4 times 2 is 8. Kick that outside. I'm going to rewrite this one more time so it makes more sense. I have u squared here, and then the square root of 2u plus 2v minus 2u, so it's just 2v. dv du. Kick out root 2 outside, and you just have root v to worry about. 0 to 1, u squared, and then we have square root of this is going to be v to the 3/2 divided by 3/2. From 0 to 1 minus u du. 0 doesn't give us anything. Kick 2/3 outside. 16 root 2 over 3. 0 to 1. And you have u squared 1 minus u to the 3/2 du. What else? So now you do, you can do u substitution because it's u, right? But, no wait, how would you do this? It's integration by parts, right? Yeah, you can. It is a trig sub. It's a beautiful problem from trig sub. Let's review some trig sub. Why not? It's a beautiful trig sub problem. We haven't done that for a long time, right? So that's going to be 1. Let's call this u. And then this side must be 1 minus u squared. Oh, but we don't have a square on u. There will be a root u there. Yeah, there will be root u here, and then no, I'm just gonna make it worse. Yeah, you can always use Wolfram. That's given.
What about on the test?
Is there any other way we can do this easily without using by parts?
I mean, FOIL in the u squared.
You gotta do this by parts twice. And I mean, obviously, what else you're gonna do is just do it at home.
Wait, why can't you foil in
You can't foil because it's a u squared.
the... Or,
3/2, right?
Wait, what do you mean?
oh, no, wait, yeah, no.
No, but can you like just throw the u squared in there?
Again.
I don't follow.
That's technically...
This thing looks like this. Square root of 1 minus u cubed. When you multiply u squared underneath, you're going to get the square root of u to the 4th 1 minus u cubed. Now what?
Foil. Just
Okay.
throw it in
Square root of u to the 4th 1 minus 3u minus 3u squared plus u cubed.
All right, keep going.
You see, you're not getting anything.
You might. You don't know.
Out.
Yeah, it's minus
Yeah, it was. The alternate signs. Plus, minus, plus, minus. Oh yeah, minus. Yeah, the last one was supposed to be minus. So just do 2 integration by parts. That's it. That's all. Nothing you can't handle like this. The answer is not 7. If you get 7, it's wrong. All right.
Is it 8?
If you get 7, it's wrong.
Oh, yeah, he's got a point.
What?
7 wrapped into 2. Over 3.
Yeah. Good. But you know how we are in Calc 3, right? Why stop at 2 variables when you can have 3 variables?
Well, on the test, because you said this is going to be... Okay. I open up that test Monday and I see 3 variables for this problem.
I was hoping, like an idiot, that, you know, we wouldn't have to do
First we have Jacobian UVW. Partial X, partial U. Partial X, partial V, partial X, partial W. Partial Y, partial U, partial Y, partial V, partial Y, partial W. Partial Z, partial U, partial Z, partial V, partial Z, partial W. It's a 3 by 3 Jacobian determinant. So same stuff like for your vectors you did, the cross product. So the first, and then you worry about those two, and then minus the second one, and then third one. And then we have the integral, triple integral over D, that used to be xyz dv, will be the triple integral over the new region S once you complete the transformation. F will be given in terms of G, which is UVW, H, UVW, and P, UVW, times the Jacobian UVW, and then dV at the end. It's another possible tattoo that you might consider, right? It's also a conversation starter.
Other question. So when you denote the Jacobian matrix by J, it's a determinant already, but then you put another determinant around it?
Determine that's absolute value for the positive value.
So it always has to be positive.
Yeah. Determinant on top could work out to be negative 7. 7 then.
Why does it always have to be positive? Yeah, like what if the integral comes out to be negative? Without the Jacobian.
What I want to say is that areas and the volumes, positive values. But then I might be wrong there. I'll have to dig into it to see. I remember, but I think it's just because the area and volume, we get the positive values for it, just like the area under the curve, positive value. So if the previous problems took 20 minutes, these should take 35. It is absolutely the same idea, except now transformations take more effort because transformations are, you are transforming planes. So you're no longer transforming lines. So 2 by 2 case, you're transforming lines, and now you are transforming the entire planes. So, you get z equals 5, z equals 3, and then x equals something, and then you have them slanted and so on. The hope is that, the surfaces that are slanted, there will be, for what you are getting on your end, there should be all of the x equals or y equals or z equals to get you a box, so the integral becomes easy. Nice.
Oh.
We might have to evacuate.
You know there's a hole in that wall.
But not this way. No, this is not a hole. It's an electrical box. It's a box.
Is there a wire cap?
Hmm?
Wire caps like that?
Yeah, pretty much. No, it's cool. No, it's cool.
Don't worry about it.
I mean, it makes sense if you the lights that are going iffy, just trace some water there. Water and the electricity work well, so work out.
Well, I was looking for the problem before the ceiling started falling, so. This might aggravate it further. All right, let's try one of the interesting problems, see how this works. So let's say the triple integral d z dv are bounded by paraboloid z equals 16 minus x squared minus 4y squared, and the transformation is x equals 4u cosine v, y equals 2u sine v, and z equals w. This one?
Yeah. I think he's in the middle. Yeah.
Alright, that should hold.
What? It's a good many hats. Now you're gonna look. Oh, it's good.
I'm sorry. Yeah, I think I was
Hey,
thinking
just be careful. Yeah, just be careful. Straight to the left. There we go. You should see like every student now going with like.
Get started, David. Just get every religious iconography.
It's definitely got to be right.
It's gonna be fun.
Yeah.
You gotta get on
Kind of lean too much on the carpet. Lean more on the desk because it's easy to.
I mean, imagine. I think I'm selfish enough to make it hard for the cleaning people.
Yeah, that's all right. The answer is yes. The answer is yes. 4 integrals? The answer is yes. Yeah, but we're going to have 16. But like, what would you use 4 integrals for? Nothing. Zero on them? Oh, yeah. In every. What about zero density? So far. So far. Solid.
And you could make it into the triple integral. You could make it into the 4 integral side. But again, no use. No need. Do extra integration.
What is this giving us?
Which one?
The answer.
Where?
To the question, can you?
Now? Yeah.
No, like to the question we're doing, what is the answer?
Everything you need. Like, you can
For which?
switch
For
and
this problem?
then
No,
you
the last
substitute
last
this
one?
in here.
Like the last one we
Like,
did.
what does it mean?
I mean, you can just ignore the cosine being sine, right?
I don't know. You said it's just like a new type of
Yeah, but we did.
So it's x squared minus 1.
Okay.
Okay, I was looking I thought, yeah. I'm not sure what that does other than get
Fill the object with water.
just make it any easier. I thought
6 kg. 4 years worth of degrees. Wait, I don't know where to start. If you want to find volume so bad, why don't you just fill the
that
object
just
with water?
completely eliminates it.
Why do you need 4 years worth of
Nope.
He's going. Alex already answered this question.
I said the more fun thing. Should we? What do you? To show them.
Never asks you what he knows.
It does, but instead of it being something don't like some V equals W.
Yeah.
Wait, can you just check on that? That sine or cosine disappeared, just sine squared, whatever.
You are a nerd.
And then 4 squared is 16.
No, I put my notebook down and I'm blaming on she's the wrong
All right. Oh, I forgot z equals 0. Oops. Guys, I forgot z equals 0. So, what do we have? Disappear.
When I have stuff I can say if it's right or not, probably not, but he'll be fine. Horribly depressing, slightly narcissistic. That's my goal. Wait.
So we have, guys, pay attention. Maybe I should put 5 of these problems on the on the test, because just to make it proportional to the amount of people that are paying attention. Actually, no. How about 2 versions on? Oh, where's the attendance sheet? 2 versions. We'll have the regular exam and then yellow exam. Exactly. Yeah. So we have 1 on x-axis and 4 on y-axis. It's the ellipse. And this is an elliptical paraboloid. So elliptical paraboloid, that's the surface of, that's the shape. And this is the bottom. So it is a solid piece. We have our transformations, and we can plug these transformations in the problem to see what we get. So first we have z equals 0 with the w equals 0. That's the easy one, right? So we have w equals 0. Oh, I did not draw. Let me first draw the 3D. U v w, and we have w equals 0, which is actually the UV plane. So we have UV plane, which is the floor of the transformed region. And then we have the large equation, just plug everything in it and follow the algebra. So z is w, 16 minus 4u cosine v everything squared minus 4 times 2u sine v everything squared. And just follow algebra. W is equal to 16 minus 16u squared cosine squared v minus 4, and 4 is 16, and then you have u squared sine squared v. You can factor out 16 out of the entire problem and have 1 minus, and now factor out negative u squared, which will give you cosine squared v plus sine squared v. So w is equal to 16, 1 minus u squared. All of the v's are gone. And this is just on a parabola on u. So what I hope you all know that what this shape is. It's just a tunnel, right? It's a parabola. When you look in the u direction, it's a parabola. When you look in the v direction, it just looks like flat, right? So that's how it looks like. U direction, v direction. For you, u direction, v, right? So we are going to draw a parabola like this, but then that parabola just, you know, goes forward. It's parabolas everywhere like that, going forward. So it's like a tunnel the way up to 16. Easy to integrate, right? We are integrating z, which is just w. So we are going to put 3 integrals and then put, oh, I forgot the Jacobian. Jacobian UVW. And now we have, oh, we're going to cry here. Partial x partial u. That's going to be 4 cosine v. It's going to be a lot of fun. And then partial x partial v is going to be negative 4 u sine v. And then partial w is just going to be 0. Next one. Partial y partial u is going to be 2 cosine, no, that was a sine, right? Sine v. And then what else? Now in terms of this one, it's going to be 2u cosine v, and then again 0. And this is 0, 0, 1. So this is not a problem. You have 4 cosine v times 2u cosine v minus and minus is plus 4u sine v and then times 2 sine v times 1 minus 0, and then 0. Nice. This is 8u cosine v plus 8u cosine squared, 8u sine. Look how beautiful. This is amazing. Wow. Wow. All that mess. 8u. Triple integral of z. Z is w, yes.
Can you just go over the multiplication step matrix again? I'm having trouble following.
You pick the first one and then work this that way, right? Since there are a lot of zeros, nothing that 30 minutes of staring at home won't fix. dw, dv, du. Now, let's see. U is between -1 and 1, right? What's happening with v?
Did you choose that order just because? Why did you choose that order? Wouldn't TW be the
Exactly. Because that one is 0 to the function, right? Now, what are the limits for v? Do what? Well, that's what I'm afraid to say. Because it seems that the limits should be from -infinity to infinity, but wouldn't that give us... This is the tricky part now. What are the limits for v? It seems that it should be -infinity to positive infinity. We know how to deal with that. It's improper integral, but I don't see any of the e to the negative and 1 over stuff, so that can go to zeros and
What about -1 to 1?
that's on you, right?
Yeah, but also v.
Why? Because, as you can see, v is the argument of sine and cosine. That can go anywhere. Now I'm thinking, let me just try something on the board before I write it over there. If I divide y by x, and I get 2u sine v over 4u cosine v, which would give me y over x, then I get 1/2 tangent v is y over x. Does that help in any way?
Maybe. You can like.
Doesn't you bounce? No.
What? Doesn't help. If I look at the boundary,
Wait, can't cosine squared and sine squared can never be negative. Right?
yeah, well, any squared value is always positive.
Yeah, so you know it's not zero. It starts at zero.
Why?
Wow.
V can be any value. See, I can use V. I can put 1, I can put pi, I can put 10 pi, I can put 100 pi.
Oh, yeah.
They will all compute. It seems that the limits are infinities, but then what possible? I want to say that limits are, right, Nick was first in the classroom to suggest negative infinity to positive infinity. So we'll just blame Nick if it doesn't work. It looks like these should be the limits on V. Now, whether that's going to integrate is. That's going to give us infinities, right?
Yeah. I mean, is that the answer?
Infinity is never the answer, right?
No, but you get this from
So that's a 4 uw squared from 0 to 16, 1 minus u squared, and then we still have dv du to worry about. I really don't like these infinities there. So as I plug in 16, that's going to be 16 squared times 4. And then I am integrating u times 1 minus u squared squared dv du. And that's going to diverge because that's a v. Yeah, something else is here at there has to be a way to bound this this v. I don't see which equations do that now.
Is there something else in the original problem?
Not that I.
Can we do trick sum now? We gotta get 1 minus u squared.
There's nothing. What happened?
I don't know if it's gonna help. Can we do trick sum now? Just if we have to 1 minus u squared. Yeah, I know, but like, I don't know what it's not.
No, we can't. That's the last integration. Now you are picking up v from the integral, and you'll have u1 minus u squared squared times v from negative infinity to infinity. So what you're getting here is infinity plus infinity for v's, right? So this v somehow needs to be, we need to figure out the limits for v. But I don't see where the equation for that is. We tried dividing, we got 1/2 tangent v y over x which actually doesn't help. So v would be inverse tangent of 2 times y over x. Now, do we treat this UVZ like cylindrical, let's say, coordinates and say that V goes from 0 to 2 pi? Right? These are like cylindrical coordinates.
Also, what would be the difference between like pi and 3 pi? So like the rest are extraneous. Like it does go on to infinity, but like 0 to 2 pi is really the only thing that matters.
Yeah, because 0 to 2 pi would trace entire shape because these are periodic functions. So pi and 3 pi gives you the same value, 2 pi, 0, 2 pi, 4 pi gives you the same value, because period is 2 pi. So if we use 0 to 2 pi for V, that to me sounds like the only option we have here. Division of the equation didn't work out. 0 to 2 pi, so 0 would give us, oh no, pi over 2, that would give us infinity. Would that help? Pi over 2. Uh-huh. Meditate on this idea.
And if you do 0 to 2 pi, you can solve it.
Yeah, I know, but this is actually. I can put also. I can also put 13.7 to 15. This is why it's so much fun, right? You get a puzzle and then you have to solve. Next time someone asks for something fun. This problem, definitely.
Google it. What? Build a wall. Wall. Oh, the infinity. Oh, yeah, that one.
I think the problem doesn't have anything else there. Bounded by the paraboloid and the xy plane, and they give us the transformation. We transform the region, and since the region doesn't show V, it has to be infinite in those. I mean, other than 0 and 2 pi, I don't think we can put anything else in there.
Would that make the answer make sense?
Well, that's the only thing that actually makes sense right now. Because 0 to 2 pi traces this once.
Right. Doesn't look like it transformed over.
Well, it's like, you know, the traffic circle, and you have the exits, and you go on this exit, and then let's say you exit here.
Yeah.
Well, you can enter and then go 5 times around, and then exit there,
Yeah.
right?
Right.
I mean,
This would be.
so if it's sufficient to go around once, because we can definitely go over here 15 times, it's still the same shape.
Right.
So that would make some sense to actually use 0 to 2 pi there. I'm not 100% at peace with it yet, but it does push this forward, so I don't know. Now obviously we're not we can do use sub here, I mean whatever sub, or we can just FOIL everything and work from there. I would rather FOIL than use all the stuff. So you have 1 squared, so this is 16 squared 8 pi times 8 pi, integral negative 1 to 1, and now you have the squared, so it's 1 times u, minus 2 u cubed, and then plus u to the 5 du. Yeah, this problem, I'm not too happy with this. U squared over 2 minus to the 4th, so u to the 4th over 2 plus u to the 6 over 6, computed from negative 1 to 1. So 16 squared plus 8 pi.
That gives you 0?
Yep, which means that we have to do half of it, and we can see it's symmetric. So do half of it and double, otherwise you get 0. So it's even function. So u squared over 2 minus u to the 4th over 2 plus u to the 6 over 6 from 0 to 1, and then make this 8 here into 16. That's 16 cubed now. And we have 16 cubed pi times 1/2 minus 1/2 plus 1 over 6. That's 16 cubed pi over 6. Maybe. Okay, let's see. Oh my God, we are a factor of 2 off. I just scrolled all the way in a textbook. I found the solution. Did they fix this? Huh, they fixed this. So our solution is 16 cubed pi over 6. And their solution is this one. So our solution is 2 times that. So there is times 2 somewhere. So probably I missed something while integrating somewhere times 2. But yeah, that was it. Easy. Who said easy? So find where is that 2 times off. Or maybe they made it.
The beginning.
What happened? All right. Well, that was good. Ugh.
Can you just go back to the hour works or something?
Yeah, so apparently looking at the book, our answer is twice as much as it should be. So factor of 2 somewhere. So from -1 to 1 would give us a 0 and kill the problem. So because we are on the even function symmetric interval, we cut from 0 to 1 and double the answer. So that's not the reason why it's double. It's somewhere before in integration or transformation or somewhere where the answer should be twice less. So maybe this is not 8u, maybe it's 4u if I didn't take derivative right or something. So there is somewhere times 2 mistake. So when you're reviewing, try to find that that half and where it's. All right, well, that's it. That's your 13.7. As you can see, it's a lot of fun. We get to transform the regions a little bit. Then we have the Jacobian. Then we create. See, this is a very valuable section because you get to set up the integrals, which you can end up having the either general region or rectangular region. They can be double, triple. You have partial derivatives. So yeah, it's a lot of fun stuff. And that is it for this lecture, I guess. So we'll resume